Q inside is this area, is this right here, right? From where the top surface of my Gaussian intersects that charged rod to where the bottom intersects. That's my Q in. And if your Gaussian surface, if your Gaussian cylinder was shorter than mine, then your Q in is going to be less, right? You're going to have less charge inside your Gaussian cylinder if you choose a shorter height. So Q in over H turns out to be a constant. We call that lambda usually, the charge per unit length. The charge per unit length. So anytime we have a long, thin object, we usually give the charge in terms of lambda, a charge per unit length, instead of just saying it has a charge Q distributed over it. Okay, so there it is. So you can see this was pretty straightforward. Way to find the electric field some distance away from a line charge. We could have done the same thing if it was a cylindrical surface with charge over it. A long, infinitely long cylindrical surface that has charge uniformly spread over the surface. What do you think we could treat this as if we wanted the electric field out here somewhere? What happened to our spherical charge distribution when we were outside of it, when we had spherical symmetry? What could we do with it? We could put it all at the center, right? We just treat it as a point charge at the center. So when you have cylindrical symmetry, we can do a similar thing. We can make this a line charge. But we don't have to, because we end up with the same, we do this the same way. You make your Gaussian surface. You want one edge to be here, right? And you go about it the exact same way. That you have the top, you have the bottom. The top and the bottom, we get any flux through those? But what does the electric field look like? Looks like that, right? Parallel. If this is an infinite cylindrical charged object, the electric field comes out parallel in all directions. So through the top and the bottom, we get 0, just like for the line charge. This becomes the electric field at that location, multiplied by the area of the sides. Right? It comes out exactly the same. Charge per unit length. It's just as if it was a line charge, because you've got the symmetry, the cylindrical symmetry. What's the electric field? Let's give this a radius capital R. So this is for R greater than capital R, right? When we're outside of the cylinder. What happens if we are inside the cylinder? So this has charge on the surface of the cylinder. So what do? We draw our, this is the side view. Here's the top view. Now we're drawing, we want to know what's the electric field at this location here, right? In here somewhere. So we draw our Gaussian surface there, and we would draw it there, inside the cylinder, right? Where we're interested, the point of interest. So what do we get? We get EA cos theta over the top of our Gaussian surface. We have to look at every side. EA cos theta over the sides. And what's the Q inside of our Gaussian surface? 0, right? It doesn't have, our Gaussian surface, the blue cylinder is completely inside of the other cylinder. It has no charge inside of it. All the charge is on the surface of the bigger object, right? Like if all the charge was on the surface of this room and we had a box inside the room, we said, what's the charge inside the box? 0, right? It's all on the surface of the room. The box would have to contain one of the surfaces of the room. So it has no charge inside. Q in equals 0. So that means that the left side of this equation has to add to 0. And so that means that the electric field has to be 0 in there. If you have a sphere with charge uniformly distributed over the surface of the sphere, and you're inside the sphere, what's the electric field going to be? 0. We did that with mass also, right? If you looked at, if you had a planet, a hollow planet, all the mass is in a shell around the outside and it has a hole in the middle, and you're in here, force of gravity acting on you, 0. Or a real planet, if you're in here, if you're inside the planet, you want to know what's the force of gravity on you. It's actually only the mass inside of your radius contributes, right? This mass contributes. Everything outside your radius cancels out. So you end up with the force is G, M inside, M over R squared, right, where this is R. Maybe I'll call that M2 just to make it a little different. Only the mass inside of your radius contributes. Everything else cancels out. It's the same with electric charge. And Gauss's law is a quick and dirty way to show that.